Okay, let me begin. I think those who have missed, we have completed already with the important type of asymmetric key algorithms, and we have done one type of symmetric algorithm. Probably all of you remember, we have completed, those are attending regularly, we have completed the Diffie-Hellman as well as the RSA. RSA could be used in your digital signatures. Your Diffie-Hellman is nothing but just a key exchange algorithm. It is not basically a what do I say, an encryption or a decryption algorithm. It's just a key exchange algorithm. And this RSA as well as Diffie-Hellman are both asymmetric key algorithms. Under the symmetric key, we have seen one algorithm, that is the data encryption standard. Now an advanced version of would be your AES, which is my part of the discussion today. So what could be the drawback of your DES is the key size. So the key size would be a simple drawback. Though you have a triplet DES as well as what is that? Double DES, but still what happens in this triplet as well as double DES is the processing time would be very, very slow. So what they did is they went on with one more algorithm. Obviously, IBM were the derivators of all, inventors of all these things. So they went on with one more algorithm, that is a symmetric key one. Sorry, a symmetric algorithm itself. That is your AES, which is an extension of your. I can say it is extension of your data encryption standard. What we call it as the advanced encryption standard. Am I audible? Rakshak, am I audible?
Yes, ma'am.
Okay, fine. Basically, what is that we try to incorporate here? We try to incorporate the data in the form of a block, or we call this as a block cipher. Either your DES or an AES would be called as a block cipher. I hope you remember what is the input to the block in case of a DES. It is 64-bit. And the keys of 56-bit in case of your DES. Though it is a 64, we make use of 56, out of which 48 bits are used in in the rounds. And you know that in case of a DES, we have how many rounds? 16 rounds. A slight modification with your AES would be in the number of rounds and the number of keys which are being generated, and the data whatever we take as an input, right? So one change with respect to your DES is your entire thing will be divided into block ciphers, and each block would be having a block size of 128 bits. Earlier it was 64, now it is 128. Now this could be one of the advantages, and hence this algorithm is also stronger as well as faster when compared to your DES. Now the highlight of your AES algorithm lies in the design of different configurations, right? So when I mean different configuration, it is based on the key size. I can go up to a key size of 256. So three variants they have given. One is with the key size of 128, with the key size of 192, and with the key size of 256. This is not there in case of our DS. We are fixed with the key size of 64, out of which we use 56, in which 48 we make use in case of the substitution, the S box as well as P box combinations, right? So if since this AES is giving me three variants, it depends on the number of rounds also, right? So I told you clearly that since the DS would be a slower mechanism to engage the processing of the algorithm. So just to reduce the number of rounds based on the key size, we have three different variants. That is, if the key size is 128, then the number of rounds would be 10. If it is 192, then the number of rounds would be 12. And if it is 256, the number of rounds is 14. Please remember this. This could be a very good question in your quiz. So depending on the key size, we have the number of rounds also been initiated. So when the IBM invented all these methodology, they went on with a reduction in the number of rounds, and these were the reduction with respect to the number of rounds, right? Because AS was designed only because the DS key was too small, right? So a quick glimpses on this. What is that? I have the entire plain text. The entire plain text is divided into a block size of each 128 bits, and you know that now your key is also of 128 bit, both at the sender as well as at the receiver. So I apply an encryption algorithm at the sender, and I get a ciphertext of 128 bit. Take that ciphertext of 128 bit with a 128 bit key in a reverse order, apply the decryption algorithm. You know that this AES is also symmetric key type of an algorithm. Hence, the reverse process has to be engaged at the decryption. Then I get a 128 plain text. It's very simple with respect to this point of view. But when I go in detail, AES is nothing but just the twice size of the DS. Just now I specified 128, but twice of the DS as an input. Now, what the trick lies in case of our AS is with respect to the key size, right? So very important. Now, this key size are processed in terms of something called as words or bytes. So all of you are familiar with when you have studied the concept of your microprocessor, you're familiar with the concept of words as well as bytes. So here, since the key size is 128 bit, so it is equivalent to 4 words or 16 bytes. So very much clear. I've mentioned here one word is equal to 32 bit, and you know that if it is a 32-bit, then how many such words I need? I need 4 such words to make it a key size of 128. Similarly, in terms of bytes, if I'm specifying, it is equivalent to 16 bytes. And since I'm going with, as a case study, I'm just going with the first one. That is the key size is of 128-bit, and the number of rounds, whatever we are considering for our analysis is 10 number of rounds, right? So in our case, we just take the number of rounds to be 10. The first one we are initiating since the key size is 128, right? Now, what should be the sub key, what should be the number of sub keys we have to use in case of AS? Now, remember, the rounds is 10, the key size is 128. What should be the number of sub keys? So totally we should have a sub key of 44. Now, this is based on how my algorithm would proceed with respect to, right? So how did I get this 44 is a trick here now, right? Now here each subkeys is of 32 bit or one word or 4 byte. So each round has 4 subkeys. So each round has 4 subkeys. So totally how many subkeys I have? 10 subkeys. Sorry, how many rounds I have? 10 rounds I have. So 4 into 10 becomes 40. But one particular that is one particular subkey, that is 4 subkeys are used for pre-round calculation. So adding that 4 subkey, so totally I have 44 subkeys. So this is the idea behind the number of subkeys in case of an AS algorithm, with the number of rounds to be 10 and the key size to be 128. I repeat, how many rounds I have? 10 rounds. So each round will take 4 subkeys. So 4 into 10 would be 40, and I have one more round, what we call it as a pre-round calculation. When I show you, when I go with the algorithms, you'll come to know where is my pre-round. So including that pre-round, I have totally 44 subkeys. So this is how we can get a 44 subkeys out of the 128 bit, right? So let me go with the normal structure of how your AS would look like. So this is how your AS structure would look like, and this is for one round I'm showing it with respect to, right? So what is that I have? The plain text is of size 128 bit. The first round is something called as add round key. So this is where we make use of the starting 4 sub keys. So this 4, whatever I have mentioned here, is used in this particular add round key. So basically, what is the operation of an add round key is just performing an XOR operation, right? So after that, in each round, concentrate, after that, in each round, I have 4 different combinations. So what are these 4 different combinations is, one is the substitution byte, which we call it as S box. I hope you remember in our DS also we had S box. Next, different methodology what we are applying when compared to your DS would be, next operation is shift row. After shift row, we then go with, I'll come in detail with respect to each particular block later. So we have a substitution byte. After that, shift row combination will take place. Next, big mix columns, and then add round key combination will take place. So here we are making use of the key in an add round combination, and at the last in the add round combination we are making use of the key. So what would be your word? See, since I'm representing the key in the form of a words or bytes, so 4 sub keys I'm using in the first particular add round XOR operation. So what could be the word? It could be the word from W0 to W3. Similarly here, it could be the next word in the series, that is from W4 to W7. So what will happen in the second round? In the second round, I'll make use of 8 to 8, 9, 10, 11. Then in the third round I make use of similarly till 10 round I'll go with respect to the keys. So totally I have a 40 key here and plus 4 sub keys here. So totally it is becoming 44 sub keys, right? So what operations I have here inside is a substitution byte, a shift row combination, a mix column combination, and a add round key combination. So this has to be taken care. How many times it has to be taken care? uh, 10 times. So if this is 1, so next 9 times it has to get operated, right? So in round 2, just now I mentioned how many sub keys I am going to use. So where I'm getting all these particular sub keys, it is through the generation of the by the generation of the 128-bit key. So let me go, let me complete this and go with each particular block in detail. So after this, whatever the output I get at the add round key combination would go into would be converted into the ciphertext, which is once again a combination of 128 bit, right? So let me go in general with respect to, yeah, one more change when compared to your first round and the last round is, yes, just see here I have 4 combinations here, that is shift substitution byte, shift row, mix column, as well as add row key. So one thing what we remove in the last round is the mix column combination is not present here. So that is what you need to remember in an AES. In the last round we are not making use of the mixed column combinations. So that is the difference when compared to your first round as well as the last round. The other things remains the same. So let me go into the first one, that is your substitution byte block. So if I go into the substitution byte block, so this is how we represent the input, the intermediate state and the output state. So basically what is your substitution byte? It's nothing but an S box combination. So what is the input I get to your S box? It is nothing but a 128-bit plain text. So how this 128-bit plain text will be represented? It will be represented in the form of an input array. Okay, so basically it is nothing but a 4 cross 4 table. You just imagine, if I refer this as an input array, then I am going combination from 0 to 15. So altogether I have 16 bytes, and when it is 16 byte, if I multiply it by 8, totally what I get is a 128-bit identification, right? So each column represents 1 byte. So this is how we represent the input array. Similarly, how we represent the output array? The output array is again in the same fashion, 4 cross 4 itself, wherein which I go with uh, out of 0 till out of 15. So this is how we represent the output array, and I have an intermediate stage. Once again, an intermediate stage is also 4 cross 4. Just now I told you it is 128-bit plain text is represent in this particular format. And what do I have in each particular column? It is nothing but indicating you the state array where we are storing the output of the substitution state in this particular format. What do I indicate by this is, the first column indicates that I have a 0 byte of the input array, right? So this is the representation of your array as well as the output. Similarly, how we represent the key is, just be imaginative now, because my diagrams are very much simple. I have not drawn some complicated diagrams here. So please be imaginative. Once again, a key is of size 128-bit. I have to expand this 128-bit, which is of 4 words, into how many keywords? That is 44 words. You know that subkeys are 44 subkeys, right? So initially it will be W1, W2, W3, W4. So each column is nothing but we are one particular what do I say? One particular word, right? So that I have to expand into 44 words. So this is how we save the keywords. So once again, each is of how many bit? 8 bit. So totally I have 16 bytes. So 16 bytes is nothing but 4 word, and this I have to expand it into omega naught till omega 43. Why? Because omega naught till omega 43 is nothing but a combination of 44 words. Now let us analyze how your Xbox indication go with respect to. Just recall your DS algorithm. If you just recall yesterday's class, what we did, your 8 inputs, see basically your Xbox is nothing but your compression. So your 8-bit input was converted into 4-bit output, how we were doing that, the intermediate four levels, we are taking it as column, and the last two we were identifying it as a row. So whatever the value we get in the decimal, that particular location, for example, second column, for third row, if I indicate, so whatever the data is there, that data I would once again convert it into binary. For example, if it is mm, decimal 8, that I convert it into binary, that is 1000. So that means from 6 bits I'm just converting into 4 bit, right? So this was in case of our DES. Similarly, on the same fashion, remember, each is of 8 bit in our what do I say, 8 bit in each particular uh, block, sorry, in each particular row as well as column. So first 4 bits will represent the row numbers, and the next 4 bit will represent the column numbers. So the first 4 bits would represent the row number, and the next 4 bits would represent the column number. Remember, everything is in a bit fashion, right? So now this output is also an 8 bit, right, where I have to store this 8 bit once again in a state array. Here I call the state arrays to be just S. I'll call here it has S dash, right? So what should be the size of this S box in case of our AESs? Now be imaginative, since I could not draw a 16 cross 16 array. The size of the S box in case of our AES would be 16 cross 16. Why 16 cross 16? You know, because I have to take in that 16 cross 16 only what is the data present. From that data I have to convert it into an 8 bit. Now for example, if this is my 8 bit, get that particular 8 bit from that row and column, and I convert that. Now for example, if this is my 8 bit input, so 4 bits are read for row and 4 bits are read for column. So first decimal conversion would be from the binary to 0, and this is 5. So where I have to get the value from the 0th row and in the 5th column. So now for example, if it is 52, then I have to store this in a state array as 52. So how do I represent 5? 5 is nothing but 0101, and 2 is nothing but 0010. So this now will go as an input to my next particular sequence, that is into the, yeah, I just completed the substitution byte. Now it will go into the shift row combination. So just now you have come out with one block. That output of that particular block is now entering into where is that? Yeah, 16 cross 16 combination. That output now I am feeding it into the shift rows. Now basically what will happen in a shift row, remember, to a shift row, what is the input? The input is once again, see here, it is a 128 bit with the key. It has performed the XOR operation, and to the substitution byte, that is to the X box, the input is 128 bit itself, and the output just now what we got from the state array is once again in 128 bit. Now that 128 bit has to go to the shift row block. Now when I go to the shift row block, simple maths, simple circular shift concept I'll apply here. What is that? I'll perform depending on what is my row. If it is row 0, then I perform 0 bit circular shift. If it is row 1, I perform 1 bit circular shift. If it is row 2, I perform 2 bit circular shift. Similarly for 3, right? Why I'll stop? Because it is a 4 cross 4 combination I'm having, right? So here just I perform a circular right shift by 1 bit. Here I perform by 2 bit. Now the resultant of this shift operation is going into the next block. What is my next block in the sequence? My next block in the sequence is the mix column combination. Remember, this mix column combination is only present from first round to the ninth round, not in the 10th round. First round to the ninth round it is present, not in the 10th round. So I'll go to the mix round combination. So when I go to the mix round combination here, this is the output of my shift row, right? I have got it in a form of an array, state array, that is 4 cross 4, that I'll feed it into a mixed row combination array. What is this? This is nothing but an multiplication operation which is based on a predefined matrix. So the predefined matrix what we make use for this mixed column combination is 2 3 1 1, shifting with one position. This is the 4 cross 4 predefined matrix what we use. Remember, this is a 4 cross 4 multiplied with the 4 cross 1. So whatever the output I get is once again a 4 cross 1 result. So where that has to be stored? That has to be stored now in once again in a state array as an output. Now this output will be fed, this output will be fed as an input for my next round. What is my next round? My next round is your add round key. Yeah, add round key, which is basically your XOR operation. So how do I do the XOR operation? I hope I'm not repeating, going back, and I'm not repeating. So I just want you to be very much careful with whatever I'm identifying, right? So after performing this, now whatever the result I have is in this particular array. After performing my mixed column operation with the predefined matrix, so I'll go with this particular output, which is stored in the state array. Now that is given as an input to your next block. So I have a state array output, that is the mixed column, XOR with what? The remaining keywords. This is for the last round I'm referring with respect to. If it is for the first round, it will be uh, W8, W9, W10 as well as W11. So this should be W um, uh, 8, 9, 10, and 11 for the first round. Sorry, I've written wrong. So if I perform the XOR operation, whatever I get is an 4 cross 4 matrix. Remember, it is nothing but each is of size 8. So 8 into 8 is nothing but, once again, sorry, what do I say? 1 byte. So 16 such bytes are there. So 16 into 8, whatever I get is 128 bit size. So after completing the first round, then whatever I get as the output is a 128-bit ciphertext. This I did only for the first round. So like this, I have to repeat 9 times, right? Only in the last one, I'm not using this particular operation. That is the mixed column operation. So this is how your AES algorithm would proceed with. Right. So with this identification, some of the advantage of your AES would be basically it is implemented both in hardware as well as software. So hence a very highly secured protocol, as well as you have a variant with respect to the key size, that is 128, 192 as well as 256, and depend upon the number of rounds also. So the rounds would be 10, 12 as well as 14. So hence this makes it to be one of the good algorithm where the hacking is not possible. Coming to the disadvantage, of course, each has its own disadvantage. Here we are using simple algebraic structure. Yes, if your predefined matrix is known, definitely anybody can hack this particular algorithm. So hence it is using a simple algebraic structure. So every block is always encrypted in the same way. So if the first block is hacked, it's very easier to hack the remaining blocks, and very hard to implement in the software. So this could be the disadvantage with respect to your AES. Once again, we can have a variations also here. Only thing is, when it comes to coding part, definitely it will be a little bit tedious, but still your attacker can decide upon these particular key size, and decide upon this particular predefined matter can hack. So hence both your DS and ES would not be so efficient type for your symmetric encryption method. I think probably cryptography people know. We have something called as hash functions, we have RC5, etc, etc. So many encryption standards are there. Maybe advanced standards we can use for the application point of view. So depending on what application I'm referring with respect to. So this is how your DS algorithm would proceed with. So if a question is asked with respect to your symmetric key algorithm, it could be either the explanation of your DS algorithm for 10 marks or your AES algorithm for 10 marks. So please identify each block properly and refer it with respect to what is required in each particular level. So what is that you have to remember is this particular concept. Probably this will help in your quiz. Is it fine with respect to the AS algorithm? I was fast. Yes, anybody please acknowledge. Hello.
Fine.
Yeah. Um, I think I have left out with 1 minute. Can I end the session and start at 3:40 with your presentation? I'll be circulating this notes and I'll do some quiz part. Is it okay if I Yeah, another 10 minutes I have. Shall I go with the quiz part? Yes, are you there?
Yes, ma'am.
Yes, ma'am.
Let me see those who attended my class. Can you manage with the quiz? So shall I go with some quiz? Okay, I'll just remove this. Yeah, some problems I have. Let me quickly go on to those problems. Yeah, those who are listening, please read the first question. I have just another 8 minutes. Okay, he is asking you to encrypt. This is a simple concept. He is asking you to encrypt a message by name extranet using your transposition method using the following key. Don't see the solution. Go through the question first. So the data is extranet. You have to encrypt using transposition method. He has given the key as 35214 for the cipher text, and for the plain text he has given the key as 12345, very common. And yeah, he is asking you to use Z as a bogus key. I hope you know what does a bogus key refers to. Remember, we had used dot or dash in case of our transposition method while we were converting into matrix. Same thing. He is asking you to use that. So how do I represent a plain text in this particular format? Where to fill these blocks, whatever the matrix, I use ZZ. Now I have to convert it into a ciphertext. He's asking me. He has given me the key to convert the ciphertext. That is 35214. So in that fashion, I'll write. So where is three? For three starting with T. Then I have five. I have A. I hope you know. So is it simple? So this is how you can encrypt. Given any message, given the ciphertext, you can convert it into a plain text using your transposition method. I think this is very simple for you. You can go with this. Yes, the next question is, he's asking you to calculate the value of symmetric key using your Diffie-Hellman protocol. Given your G is, it's not G, actually it is Q, sorry. Q is 7. I hope you know Q is a prime number. And what is P? P is nothing but a primitive root. P is 23. X is 3. What is X? Yes, anybody? What is X? Forgot Diffie-Hellman. Hello? Are you able to hear me? Hello? Am I
Ma'am.
audible? Yes, what is X? X
Prime
and
user's key,
Y?
private
X is
key.
the, yeah, private key of the user A, and the Y is the private key of the user B. So he's asking you to find what is the key exchange between the sender as well as the receiver. I hope you remember the formulas. Use the formula and try to find what is the value of K. Probably I'm circulating this, so please go with the simple calculation, and of course the answer for K is 10. So similarly, I think I did this problem in my previous class. Now we are data is, I love CCN. Anything can be given, so please encrypt based on whatever the requirement they have given. It is an he's asking you to use the RSA as a crypto system where P is equal to 13 and Q is equal to 31. Two prime numbers he has taken. Value of D also he has given. Only thing is, you have to find the value of E. I hope you remember. Either you go with the extended Euclidean calculation method, or use the crude method, which is there in my notes, to calculate the value of E. Then go on encrypting this I love CCN into what is that, from 0 to 25. See, make sure, don't get excited. He has given it from 0 to 25. Sometimes they may ask you from 1 to 25 also, oh, sorry, 1 to 26 also. So be careful from where to where he has given. So I think you can proceed with the algorithm if you remember. Like, okay. So next I have a method on based on Caesar cipher. I hope you remember what is a Caesar cipher method. He's asking you, yes, go to the fourth problem. I think I have another 5 minutes time. Probably quiz I'll go into the next class. Yeah, he's asking you to use the shift cipher with key 15, and is asking you to encrypt the message society. Okay, anything it could be. I have taken as a example society. So what I can do, basically it is a Caesar cipher method. Based on the shift cipher, I can complete this encryption. What is the key as given? I hope you know. It's a round robin fashion. Please convert these equivalent values with respect to A to Z, and where he is starting A to Z, I think from 0 he is starting A, Z with 25. So if you just count in a lane, S is 18. So 18 plus 15, the total is 33. I think I am there. Yeah, 33 minus 26 would fetch me 7. So what would be 7 in your sequence? It is H. So S is converted into H with a key size, with a key of 15. So like this, I can convert what is that, plain text into a cipher text using the Caesar cipher method with a key size of 15. Okay, so let me stop at this point. I want everybody to log in at 3:40. Those are giving the presentation. Is it fine? Was it today's session okay?